morning, everyone. My name is Christopher. I work for TE Connectivity, based in the UK, where we have our fiber optic facility in the south of England. My presentation today will be how we can run fiber optic electronic packaging, and we will open a new design possibilities for low and zero satellite applications. Fiber optics digital processing technology drive a modern application for requiring high-speed broadband connectivity. We will review the critical role of fiber optics and how combining multiple fiber optics connectivity and optical flex circuits, how we can to allow access to high-speed data transmission. Which will actually have quite a substantial impact in cutting weight and space within these processor units. So fiber optics has been around for many years, especially in the telecom industry for the last 20, 30 years, and gradually stepped up in terms of the moving into the rugged application role. 15 years ago, I personally participated to introduce fiber optic in oil and gas industry for offshore wells, which, believe me, it's a very harsh environment in terms of monitoring high pressure and temperature systems. And moving on into, obviously, the world of ground vehicle, the civil aviation, military aviations, and gradually going up to space nowadays. So why fiber optics? Maybe some of you really understand the benefits of the fiber optics. The main objective, especially in high-speed data transmission, it's the virtual unlimited bandwidth. With nowadays transceivers going for 100 to 400 gigabit per second, this really moves very much faster compared to copper solutions, and more importantly, for longer distance. Obviously, in the application of a space environment, the distance is not really a few kilometers, but it can reach a few hundred meters, which is key to achieve this high data rate over the distance. And especially with the low loss property of fiber, you can keep this very high speed, high distance with a very low signal to noise ratio, which is quite key for this application. Another very key parameter for space, it's the weight, and using fiber optics, you really cut the weight of the system, as a glass material really represent a quarter of the weight of copper, which obviously for, again, satellite application, it's very key, and keeping a very, very small size of the system. Because obviously we are in a very confined space environment, so the use of fiber optics is very important for high-speed data processing. Signal integrity, it's also a very important point. So having glass material, the signal when propagating along the fiber really do not jump from one fiber to the other. The only way of doing this is by fusing the two fibers together, which is not the case for this application. Only if you want to use combining and splitters application. They are mainly purposely manufactured in such a way you have this signal jumping from one fiber to the other. But by just putting two fibers together, this do not happen. So you have a certain security within the communication there and the signal integrity. Which is also related to crosstalk. Two fibers very close together do not talk to each other. So if you can translate a bit more into the art of a satellite, the key point here is how do I achieve this very high speed processor assembly within this very confined environment. So in this subsystem, the choice of material are very key to actually complying with the outgassing requirement. So by choosing the right fiber with the right components and the right material, but also the transceivers associated to it, it's very key to actually to be very compliant with Schutz outgassing level. Lightweight, again, if you compare to copper and the space environments, high-speed components are very key in terms of maintaining the weight, not only on the fiber side, but the choose and the way you choose the optical connectors by minimizing the weight of these connectors and introducing as much as possible many fibers in not only one connectors, but in the termini itself. So it's multiplying the numbers of fiber within these termini and minimizing the size of this connector within your unit. High reliability, of course. Once the satellite is launched, there's no way you can really repair the system. It's very similar to oil and gas. Once you actually deploy your system, it's non-retrievable. So you need to ensure the high reliability of the system, and qualification requirements are pretty stringent to achieve this, and I will talk about this a bit later in the presentation. And of course, radiation compatibility. Radiation may have an impact on certain lengths of fibers, and choosing rad-hard fibers, it's key to keep the optical performance of your optical link, depending on the altitude of your satellite, but it's a key parameter for this system. If you are moving a bit more in the processor unit itself and related to the data and your payload for the optical performance of your digital processor system, the high density of the fiber, it's again key to keep the weight to a level that is very competitive, and also the innovative way of managing certain numbers of fiber, it's very key, and I will explain this a bit later in a presentation as well. The need for miniaturization, again, to gain this space and keep your system very small, it's in adequation with actually the way you're managing all this fiber by keeping the optical performance, so no stress within the unit. It's also key. The reason for that, a stress fiber will be relieved and will be moving your optical performance if your environment will be completely varying in terms of pressure variation, and your optical length will have an impact on this. So having a stress-free system, it's very key. And finally, your subsystem having been assembled together, it's much easier to drop this subsystem into your unit as a plug and play. So these systems are already tested before you actually put it in the system, getting time in the assembly time and the final test itself. Moving from the inside of the processor, so for a system where you have intercommunication between two processors or to your payload, intercommunication, it's also by having optical fiber harness system, you are keeping this high-speed communication with the required material to also still complying with outgassing requirement. So keeping in these little harnesses is how can I add up more and more fibers by still minimizing the size of this system and keeping the weight as small as possible. So historically, for different applications, I may know for space system, the way you design fiber optic harnesses, so on one hand you have multiple fibers, and then on the other hand you have to break out all your fibers in different direction and different type of connectivities so on over a certain length of fiber. So how can I really have a similar functionality within my satellite, which is very obviously different compared to a ground system where you have more space to do so. And you can end up as well, when you look into more into your unit itself, we want to avoid having to place each individual fibers within your unit by plugging them one by one, routing them one by one within your system. Handling will be more and more difficult as you increase the numbers of fibers, and also keeping it really stress-free, as I mentioned earlier, to avoid further signal degradation of your temperature or the environment after that. So really what is available out there, what technology can be available out there to actually simplify this process. So at TE, we've been working for more than 10 years now on optical flex circuits, which are a key technology to achieve simpler, lighter, more space, reducing completely the space that you need to manage multiple fibers in the very, very confined space environment. The way we make this optical flex, we've developed fully automated systems to be able to run this into productions. We are able to lay individual fibers one by one in a very already detected footprint and routed those fibers from the input area where we want this fiber to come in to the output coming at the right location within the processor system and the footprint. This way, it's each fiber are laid on in a very controlled manner, ensuring the completely stress-free fiber by really controlling the band radius of each fibers to the acceptable level for which you will not degrade your optical signal at all. So virtually these systems are made to have a low impact on your total optical loss of your system. Only the connectivities at both ends will have a slight impact on this insertion loss, which is this ensuring 99% or 98% of your optical transmission. And again, as mentioned earlier, these systems are pre-routed, pre-connected, and pre-tested, so make it easier for the system integrator to drop this already tested system into each processors. The other way, which is slightly different way of doing this design, is you not only think of designing in a 2D dimensions, but really in a 3D dimensions now, which give you this ability to increase from a few tens fibers to a few hundred and up to a few thousand fibers, in keeping the footprint of the system to a very low size and dimensions. So introducing fiber optics in these high-speed processor systems, it's a real game changer for this aircraft. And again, because the fiber it's 5 times lighter than copper solutions. You keep the bandwidth very high, which means compared to electricals, you minimize the numbers of wires within the systems. And of course, EMI humidity, which the fiber is completely immune for. You don't have the need for shielding, which minimize also have an impact on the total weight of the system. If I go a bit more in details within this type of concept processor unit, if I get there. Here we go. You can see on the right-hand side two really simple examples of optical flexes, which are terminated by their own little fiber optic termini, where you introduce multi-fiber, 10, 12, 22 fiber in a single termini, where you can plug them into single termini connector or multiple termini connectors. So here again, to minimize weight and increase space saving within the unit. The example you have there, it's a fully passive system where you can achieve interconnections or interconnectivity, cross-connectivity within your fiber, shuffling your signal, having one fiber coming in on the same termini but going into a completely different output where you want that signal to be within your system. But also some of these legs, which are the little parts coming out of the orange area, which are kept on, for example, for space compatibility here. You can also have some of these legs directly terminated to your transceivers. So these optical flex can be directly integrated into PCB, where you have your transceivers, your receivers, and then you can dispatch your signal in and out this high-speed processor, intercommunicated with other processors on the other hand via this optical fiber harness, and all within the acceptation of weight, length, and space. On the left-hand side, you can see maybe at the bottom here, I can't point unfortunately, but at the bottom of the box, you can have one single termini which have 24 fiber optics. The black conduit you can see, it's also a space compatible, radar compatible conduit, which will interact to the next unit next to the payload, for example. And you can see the stack up of different units here, so you can multiply the numbers of fibers and really open the way you're doing the design of this architecture within the optical high-speed processors. Different ways of having different type of connectors, obviously depending on your need. Whether they are single connector, very small footprint. We're talking a connector with a diameter of 13 millimeters, which can have up to 24 fibers, for example, and a much more complex, again, depending on your design, where you can stack up all your optical flex, but having all your fibers going through the system on the input and output side in one connector only. So again, space saving, it's of the essence here. Feel free to come by our stands and we can detail this a bit more. What does it take to have all this system compliant with the space environment? Obviously, you have to really test each individual component first with the specification, both in terms of radiation, making sure your system is stress-free. So through this environment, your optical signal needs to remain within the acceptance criteria of not only the component itself, but within the overall system together. So keeping an eye on the performance of the overall optical power budget of your system, it's also key here. So you start by testing each individual components, and then you move to subsystems, whether it's temperature variation, thermal TVAC testing under temperature, obviously for the compliance of outgassing, a shock and vibration level. We can treat several thousand of Gs, which is a quite stringent test here. Bear in mind to keep your optical loss to an acceptable level. You have to keep the alignments of this fiber within half a micron accuracy. So it's a very challenging system. And again, at the end, you want to test on the other side your optical transceivers and receivers to comply with the 10 gig or 28 gig data rate, also across all these different environmental variations, which are also keys. A little graph to show an example of many hundred and thousand cycles and how the optical signal vary across the systems accordingly. Finally, We, again, depending on your configuration, the size of your satellite and the solution that you have, whether you have a need of only 12 fibers, for example, optical flex can be very, very small for very small digital units, again, whether it's for Earth observation system with high definition video system, or certain very high numbers of fibers where you would need to have this bigger connectivity, having one single connector managing hundreds of fibers in one go. So we have a variation of optical termini in our portfolio, all space compliant, and also some different ways of doing the connectivities here, whether it's a push-pull system, rectangular system. It really depends on the size of your final processor and so on. And the optical flex being the heart of the system to achieve this quite complicated design and keeping this high-speed data processing requirement. This finalizes the brief discussion on this presentation. Again, feel free to come on our booth in D17 to discuss this system in much more detail if you require more information. Thank you very much.